So yes, I'm David Ham. I'm from the Maths Department at Imperial College London, where I run the Firedrake project. Slightly relevant to the conversation we're having just before we started, I'm also the chief editor of a journal called Geoscientific Model Development, GMD, which if you're working in this area, you might have published in. If you haven't, you should. Of course, Firedrake's a big project, and so my name's on the front of this. That's obviously not how it works. There's a small army of people who deliver Firedrake. These are the people whose jobs on the whole largely consist of putting stuff into Firedrake. On top of this, there's a whole bunch of other users who sometimes commit something back as well. So most of these are PhD students and postdocs at Imperial. Lawrence is the other key person behind Firedrake. He has defected to NVIDIA, but he still seems to be quite active in Firedrake, so we're happy about that.
Where
Where in NVIDIA?
Yeah.
So, I mean, physically from his home in York. What he's actually doing, as I understand it, is NVIDIA have essentially decided that NumPy is a beautiful abstraction for GPUs. Because the thing about NumPy is all of your array pointers are protected by an object, and all the accesses have to go through this object. So now you can imagine seamlessly offloading your NumPy arrays to the GPU, because you can just intercept the API calls. And the way that people were already encouraged to write NumPy code, like writing NumPy is a bit like the way you used to be taught to write MATLAB code, right? You have to vectorize everything. And that's also very GPU friendly. So essentially, NVIDIA have come around very much to the idea that the proportion of the world who are going to write a GPU language is vanishing. And so they need to find programming models that look like the way people program in order to use their GPUs. And that sort of thing is part of that. It's in the same team as Graham Markle. Graham Markle is Mr. Number. For those of you who know Number, that's just compiled Python. Graham Markle was actually the first Firedrake PhD student before it was even called Firedrake. But I digress. So what's the problem that we're solving? So essentially what we're doing is numerical solution of partial differential equations. And so this turns up everywhere. Firedrake is pretty heavily geosciences focused because of where the people involved come from, essentially. And so PDEs in geosciences turn up in atmosphere, ocean, cryosphere, solid earth. I've just come back from 5 months at the Australian National University working with people who are using Firedrake to do mantle convection. So all the way across the scene, because basically anytime you've got a continuous system, Mr. Newton's going to knock on the door and tell you that it's described by partial differential equations, and then you're going to inconveniently find that we don't have analytic solutions in all but the most simple cases, so you need a numerical solution. And that's the game that we're playing. And so how do you do that? Well, first of all, you do physics. So the first line on here, I think I draw a pointer. There we go. Old-fashioned pointers. So the first thing you do is physics, and so you come up with a PDE. So I'm saying a residual because I'm a nonlinear finite element person and we talk about residuals, but that's just the partial differential equation. And it has boundary conditions, and it's probably got parametrisations and stuff shoved in it because your partial differential equations don't either describe everything or don't resolve everything. So you have turbulence parametrisations and you couple to chemistry and all that sort of stuff. That's physics, right? That comes up with the problem you need to solve. And then you need to actually formulate something that you can compute. So there's a whole series of stages to do that. So you have to choose a discretization. So for reasons that will become apparent, Firedrake is a finite element-based system. So we support finite element discretisations. And so you have to choose finite element spaces, and you have to choose how you're going to integrate the equations. And what that's going to do is it's going to produce a big discrete system. So if it's a linear partial differential equation, what you get is a matrix and a vector, and you have to invert the matrix onto the vector. If it's a nonlinear system, well, the dirty secret of all of mathematics is that we don't know how to solve nonlinear problems. So the answer to that has essentially not changed since Newton and Raphson originally came up with this idea. And so what we do is we do Newton on that. And so we need linear solvers and So what they don't teach you in your undergraduate linear algebra class, not even your numerical linear algebra class, is that most of the performance issue isn't in the nonlinear solver. Most of the performance issue is in the preconditioner. And so that sits on top of this as well. We'll come back to that. And then you actually have to write this out as an enormous loop stack. And now I've got an algorithm, and now I can write code, but that code has to be parallel, and it has to be plugged into the solvers. So all of that stuff, this is what I've got. And this is where I'm doing the science. So every time I make another decision about my equations or my solution, I go all the way down through here. Every time I have a bug, what I can look at is, if you're the unified model of the Met Office, 2 million lines of Fortran, and you have to reverse engineer out of that what the original equations were and work out what the problem with your code is. This is horrible. Right? The consequence of this is that writing numerical solvers is an enormously labor-intensive, error-prone, frequently tedious job. Right? You have, and it's frequently out of reach of small research groups. If you are someone like the Met Office, you can do it, but you can do it because you literally spend millions of pounds a year on just producing the software. And then you do it all again for the adjoint. So it turns out, and this is hopefully not a surprise by this point, because I know you've been doing some data science stuff at this talk. It turns out that most interesting problems in science and engineering are actually inverse problems. So it's not, I just wanted to set up the system and see what happened to it. I have observables about the system, and I want to either know what that was caused by, i.e. no sensitivity, or I want to optimize the system to recreate it. And both of those involve differentiating the model, and the efficient way to do that is to solve the adjoint PDE, which, for those of you who haven't encountered adjoint PDEs, is mathematically exactly the same as backpropagating the PDE. So we have to be able to do backpropagation in the same sense that the machine learning people do. So we need all of that. And what Firedrake does is makes most of that go away. So we can't make the maths go away for it, right? So you have to choose what it is you want to do. But what we can make go away for you is the implementation. So having written down the maths you want, we can generate, compile, and run the code automatically in parallel and give you an answer. And then, as we'll see a bit later, you can just say, oh, and now differentiate the whole thing. And we can do that for you as well. So that's the promise that's on the table. And what this is, primarily, is a productivity tool. Primarily what people who use Firedrake for science use it for is because they can go from knowing what problem it was they wanted to solve to actually having a solution in a vastly smaller amount of human effort than would be the case if they were writing a lower level interface. It's also true that we can do some cool performance things along the way there, and there are circumstances in which we're also way faster than most handwritten code. But actually, the vast majority of users don't care. The vast majority of users want acceptably good performance in parallel for as damn close to zero programmer effort as can be achieved. And that's the niche that we live in. So, how does that work? So, the way we do it is, in maths and computer science, we essentially have one trick. The one trick across all of maths and computer science is to reduce something to a previously solved problem. Right? It's called a composable abstraction. So what we do is we make a more complicated structure out of simpler structures, but we do so in such a way that the more complicated structure itself has no mathematical properties, so that I can repeat that process as many times as I need to make this huge stack. Because basically that huge long list of steps I gave you at the beginning is a series of processes, all of which have to be stacked up on top of each other to give you a final computation. And that's the game that we're doing. So, we're going to need a PDE to do this, and the PDE I'm going to throw up is the Burgers equation, named after Jan Burgers, who is a professor of mechanical engineering at TU Delft in the Netherlands. And what this is, for those of you who haven't seen it before, is just the advection equation for velocity. So this is the rate of change of velocity is given by the advection of velocity and the diffusion of velocity. And so this is the simplest thing, which is kind of sort of a fluid equation. And the thing that's sort of spectacularly missing compared to fluid is where's the pressure? And so the Berkeley's equation is essentially the equation for an infinitely compressible fluid. So the fluid never pushes back, so you have no pressure terms. So I'm just putting it in here. We'll see it again later when we start playing with the code, because the Berkeley's equation is, well, it's a fluids equation which people actually use for studying phenomena in the geosciences. It was originally used to study the phenomenon of waves getting steeper and breaking, because that's what happens in the solution to the Berkeley's equation. But it's a time-varying PDE, and it is a nonlinear PDE, and it's about the simplest thing that's a time-varying nonlinear PDE. So that's the one we're going to do. And I'm going to give it a suitably simple boundary condition. And because I'm a finite element person, so we can't do a finite element course in here. So I'm going to have to apologize. If you know nothing about the finite element, then you should let the finite elementation bit wash over you. And if you know a bit of finite element, then this bit will make sense. So when we do the finite element method, essentially what we do is we multiply it by an unknown function, which is how we test for equality. So we say this equation is true if the equation is satisfied for all such functions in a suitable space. We integrate the equations over the whole domain, so we're testing everywhere in the domain. And sometimes we integrate by parts. So over here I've integrated by parts. The reason why you integrate by parts is so that I can use functions which are less continuous than I would otherwise need to do. Because if I'm going to have a second derivative in there, I need some very smooth functions running around. And it turns out that if I integrate once, I only need continuous functions. So that makes my life a lot easier. And so this is semi-discretized. I've still got a time derivative in here. I make a choice of time discretization. This is just method of lines. So if you've ever done any numerical ODEs or numerical PDEs, I just choose my favorite ODE solver to step through time. My favorite one in this case is backward Euler, merely because it produces fewer symbols. I don't recommend you actually use backward Euler in almost any circumstances, but this way I get fewer symbols. So what does that mean? I discretize the derivative as just a finite difference, and then everywhere where u occurs, I choose the new value of u. So it's going to give me an implicit system of equations to solve, because I need to know un plus 1 in order to substitute it into this equation. So that's a system I have to solve. So there's the maths. This wasn't supposed to be a maths class. There's the code, all of it. It's all right, I'm going to zoom in a minute. I realize it's not really very readable. But so on the slide there, that whatever it is, 20 lines of code is a fully functional nonlinear PDE solver. That would, by the way, work in parallel. If you MPI run that Python script, that will execute in parallel. And so what it does is simply write down the maths. What we're doing is writing down something that looks like a kind of highly specialized mathematic or a highly specialized simpy. So I get my mesh, and later on we'll see how you can use a more interesting mesh that you got from a mesh generator. And I start declaring symbolic objects. So I declare a function space, which in this case is a continuous space with second order polynomials. There are many available. I make a function in those spaces. So these are solutions. Right? These are fields, a field value everywhere that lives in that space. Here's my unknown function, which lives in the same space. Here's the symbol for x. So if I'm going to write forcing functions, which are a function of space, I need to be able to declare the symbols for x and y. So there's a symbol for x. And here's an initial condition, which I get by projecting some function of x into that function space. So actually, if you know what a Galerkin projection is, I've actually already solved the partial differential equation there. It's a zeroth order one, but it's an equation there. Come back to how that works. And then I set up initial conditions, I write down my equation, come back to that on the next slide, so I realize it's a bit small. I time step my equation, I solve my equation every time step. I get a new u, and I make u old equal to u, and I do it. So the magic happens at this point. So everything I did was I wrote down symbols, and then I said solve those symbols, and somehow I actually got a solution. So how does this work? Well, first of all, let's work out what it is I'm solving. So this is a little bit zoomed in. I probably should have zoomed that in a bit more. So this is the differential equation that we drew up earlier. This is the code. So you can see that what I've basically done is write out that PDE in text. So here I have the inner product of u plus 1 minus u divided by time step with v plus the inner product of u with now the grade u, if you're not quite reading the same way, plus mu times inner product of grad u with grad v, and because ASCII doesn't have a integral sign, we indicate integration by multiplying by the measure. So using this syntax, I can write down essentially any partial differential equation. A little bit later when we start playing, you'll see even vector valued mixed partial differential equations. So I've just written this down. And what then happens? Well, what do I need to do? I need to solve this, and all I've done is given you a Newton residual. So I need to, first of all, get the Jacobian. I need the derivative of this guy with respect to its, with respect to the solution variable. Well, that's fine because in my code, I've got the mathematical expression. And so I can do exactly what Mathematica would do and differentiate it using the computer. Just do algorithmic differentiation on that expression, and I've got an expression for the Jacobian. So all over the place, I can do symbolic manipulation of the equations before I start generating code to produce the answer. And that's one of the secrets that we'll come back to when I talk a little bit about the adjoint. So I can get those, and now I need to evaluate integrals. Well, what do? I apply my one trick, and I make it a simpler problem. So the first thing we notice, and the reason why anyone ever did the finite element method, is when I integrate over the whole domain, that's simply equivalent to integrating over every cell in the domain and adding up the result, because integrals are linear, which is great. And actually, I don't even have to know how to integrate over any cell. What I do is I make a reference cell, so I maybe make a right-angled triangle or a square, a unit square, and I work out how to do the integral on the reference cell, and I just change coordinates. Every time I hit a cell, I change coordinates. And so that's what happens here. I have a global coordinate system and a local coordinate system. So for reasons that escape me and I find really dumb, the most widespread convention among finite element people is that we use little letters for the global system and big letters for the local system. Yeah, I don't know. So here we go. So here is my change of variables Jacobian, and so I just substitute. And what was that bit? That was another symbolic manipulation of the equations, so I can do that using exactly the same mechanisms that I used for the differentiation. And actually, it turns out that Jacobian is just another one of the same thing, because the Jacobian is the derivative of space with respect to the local coordinates, and space is just a function in a finite element space. We do the same thing again. So I only have a couple of tricks. It's just if I keep applying them, eventually we're going to get somewhere. And so then what I need is these guys, which is the gradient of the basis functions on each cell evaluated eventually at every quadrature point. And it turns out in 2004, a gentleman by the name of Rob Kirby, then at Chicago, now at Baylor University in Waco, Texas, came up with a library which does that. We just say to Fiat, please give me the tabulation of these cells, and it gives me back every basis function at every quadrature point differentiated in every direction. And so I get a big tensor contraction to do on every cell. It turns out it really, really matters how you do that tensor contraction. So for the benefit of the more CS types in the room, what I've done is produced a constrained integer linear program, and I feed it to an ILP solver, and it tells me which order to use to do the variables in. So now I've got an algorithm, and what we effectively do is spew out C code for that algorithm, and we call a C compiler. And that gives us a shared object, a dynamic library. We link the dynamic library at runtime, call it, and we get back a matrix or a vector. And that we feed into another library called PETSI. And PETSI everybody knows because PETSI provides you with solvers. The thing that is that PETSI's philosophy is the same as our philosophy. What PETSI actually does is give you composable abstractions for solvers. So what we do is we don't really actually build the matrix. We give PETSI a callback that will produce the matrix, and we give it a callback that produces the right-hand side. And we can then stack up an arbitrary set of operators and preconditioners around those callbacks. And without us writing any more code, we can essentially give you any precondition you can think of. And there are people who essentially do all of their research by stacking preconditioners up in Firedrake and proving which ones are better for which sort of PDEs. So that's forward. I realize I'm going quite quickly here, but I want to get on to actually playing in a bit and not bore people with too much talking. What about coming backwards again? So as I mentioned, most of the problems that we want to do are actually inverse problems, which involve differentiating the model. Oh, and since I've got a Julia person in the room, so in 2019, Julia won the Wilkinson Prize for numerical software, which is a very big deal. Do you know who won the Wilkinson Prize before Julia?
That was, no.
We did, for doing this. What happens, so I can differentiate my model. I can also, because I have my model at a very high level, I can record everything that my model did. So I have a tape of my model, and I can differentiate it, and I can run the tape backwards, running the transposers of all the differentiated operators, and skipping over vast amounts of tedious detail. That can get me an adjoint. And if you're a user, so in order to have an adjoint, in order to be differentiating, I need to be able to differentiate something, right? So I can't just run my model and say differentiate it. What I have to do is compute a quantity of interest out the other end. And now I can say differentiate the process of computing that quantity of interest with respect to what I tell you is the original control. And so in this case, we've solved burgers, and maybe we'll just take the squared norm of the final solution and the squared norm of the initial solution. It's a silly metric, but it's one that will work. So here is my code for doing that. It's exactly the code that I showed you earlier, except for the 3 blue lines. So one of the blue lines basically switches on all the infrastructure for taping, because if people didn't want to run an adjoint, they're not going to thank you for taping the entire operation, because it's quite expensive. And then at the bottom, I say, assemble that piece of calculus I told you, and compute the gradient with respect to, and I'm going to say with respect to the initial conditions, which is this variable up here somewhere. Can't see where I've done that. So, and what then happens is Firedrake tapes everything, which gives you a control graph. So those of you who've been doing lots of machine learning stuff should start to feel very familiar at this point, because what do? We start at the bottom, and we just walk backwards up every arrow, computing the adjoint of the operation until we get back up to the beginning. So what we're doing there is exactly the same as what PyTorch has always done and what TensorFlow now does after Google realized the error of their ways. I'm not going to go into detail about how to do that. I will mention, by the way, one of the nice things about having these very high-level blocks is you can keep composing the blocks together in different ways. And one really useful thing about gradients is if you've got gradients, you can use Taylor's theorem. So you can go back and check your working when computing a gradient, because you should be able to do a Taylor expansion to two terms using the gradient you computed. And you should be able to compare that to the functional actually evaluated at an offset. And as you shrink the offset, that had better converge at second order. It turns out that that's an incredibly sensitive metric. Almost anything you can do will blow your second order convergence. And so we actually have a built-in function where you can basically just take the functional that you've said and say, go and do a Taylor test on this to make sure that we haven't done anything wrong. So, which is good. So as I mentioned, other things that are on and around this, and more layers I don't have time to talk about. There's a gentleman called Alberto Baganini at Leicester who has built the infrastructure on top of this. So if you differentiate your PDE with respect to the shape variable, which we can do, the space variable, then you can do optimization of designs, things like that. If you have a nonlinear PDE, it can have multiple stable solutions. Scarily, it can have multiple stable solutions, all of which can physically occur. So if you run your numerical PDE solver, it will give you a solution. It may not be the only solution, which means that if you try to compare yourself against an observation or an experiment, you could get something completely different and still be right. So deflated continuation is a mathematical construction for taking a solution and then eliminating it from the PDE and running Newton again to get another solution. And Patrick Fowle in Oxford has basically automated that process. In the last year, a couple of my PhD students, so Nassim Bouziani is working on, so I keep mentioning how similar this is to neural nets. Well, it turns out these days quite a lot of people would like to combine PDEs and neural nets. So they either want to have terms in their PDE which are evaluated by evaluating a neural net, or they do inverse problems, and most inverse problems are actually ill-posed. And so you tend to need to regularize your inverse problems. And almost by definition, we don't actually have a closed form for a regularizer. If we had a closed form for a regularizer, we put it back into the original equation. And so learning regularizers is a fairly common thing to do. So we have mechanisms just about there for doing that. And the other inconvenient thing about users is that they tend to want to interact with real world data, which causes all sorts of problems. You shouldn't do that. I suppose if you want to actually have any sort of impact, you must. And so Ruben Nixon Hill is working on questions like, if I'm solving the flow in a glacier and I have a whole load of point measurements out there that supposedly constrain my model, how do I put the point measurements into my inverse problem? And that's also quite cool. So it turns out people use this. So these are just some geoscience ones. So these are a bunch of models that are written in Firedrake. So other pieces of software where the PDE solver underneath the hood is provided by Firedrake. So this is where I spent my last 5 months. This is the Australian National University, do this. That one is led out of the Finnish Met Office. It's a coastal ocean model. It's also got some developers in earth sciences and Imperial. There's an atmosphere model. This Gusto is, for those of you who know what Gung-Ho and Elfric are, the new Met Office models, Gusto has the same numerics as Elfric. It's just you can implement changes to Gusto in an afternoon instead of leaving a 6-month project. So now even the Met Office run Gusto to prototype changes to Elfric. This is a group at the University of Sao Paulo doing seismic inversion. This is what I just talked about with glaciology inversion. So this is led from the University of Washington in Seattle. And this is an outfit, this is University of Waterloo, Canada. And they're doing more idealized geostrophic turbulence modeling. So that's just some eye candy to attempt to convince you this isn't just a toy, because what we're going to do now for the remaining 1 hour we've got is do some toy problems. There's a bunch of other users. We have users everywhere. We have users on 6 continents. I'd like to say 7 because Firedrake has actually been run on all 7 continents, but we don't have a permanent presence in Antarctica. I will also shamelessly plug the fact, this is a side point. I have a book about object-oriented Python, which is out. It's also freely available online. So if you are mathematically inclined and would like to improve your Python, that is out there, and it's, I think, quite cool. So that's Firedrake. That's the whistle-stop tour of me talking about it. What we're going to do now is a little bit more interactive. We're going to do some Firedrake. Because there's a lovely chap called Francesco Ballerin, who is at one of the Italian universities. I can never remember which one. He's got a long name. And he has hooked up Firedrake so that it can run in Google Colab, which means that you can point your web browser at the right address, and you'll get the Jupyter notebook will pop up, and you can just run Firedrake and do things in that notebook and have a go yourself. So that's what we're going to do now. I'll switch over to doing that in a second. So if you have come equipped, and assuming equipped, one handles X, where you want to go to is Colab. This is the URL for Colab. You probably actually just want to type Colab into your search engine and it'll drop you in there. And then I'll show you how to get our notebooks. The line at the bottom is just a reminder of what you'll need to know to get them. So here's Colab. When you open up Colab, you get this page, which is places you can open up notebooks from. One of the options is to directly open notebooks that are on GitHub. And so what you need to do is go to this page, and when it comes up, it'll just come up blank like this. You type Firedrake project in there, and you get a drop down, and what you need to choose is Firedrake project /ICCS CAM. So that is what I've written down over here, so that when you forget over the course of the next hour what to type in to find the next notebook, then that's what you do. And so when you do that, we get this list of, these are our tutorial notebooks, which have been rigged up to work on there, on Colab. And I will open SPD Helmholtz. And what you'll see in all of these notebooks is that they've got a first cell which has got this pile of rubbish in there. That is the magic that will cause Firedrake to get downloaded onto Google's Colab server and run. So the very first thing we do is run that cell, Shift-Enter if you're not. Yes, I know, Google didn't write this notebook. I promise we're not trying to hack you. You can believe me or not. So that will stand there, and over the next minute or so, it will install Firedrake. There it goes. So what are we going to do first? Well, in the Guild of Finite Element Practitioners, there is a solemn law that says that what everybody does as their first finite element problem is solves the positive definite Helmholtz equation, which is this one right here. So it's like Poisson's equation, but with an extra term. It looks like steady heat diffusion. It's also the term that turns up in your compressible fluid solver. The reason we solve this problem is not because it's a model problem for either of those. The reason we solve this problem is because if I solve Helmholtz and I solve it with this boundary condition, I don't explicitly have to worry about any boundary conditions, so my life is made easy. The reason for that is when I do my finite element thing of multiplying by a test function and integrating my parts, the surface term I get from integration of my parts, oh, that's just happened.
You? There we go.
Oh.
It's back.
Okay.
Straight down the road.
This term that turns up here has grad u.n in it, and I told you that grad u.n is 0, which means that the correct way to apply this boundary condition is by crossing off that term, and therefore I don't have to do anything. This is finite element people call this the do-nothing boundary condition. So what's hopefully happened while I've been wittering on is, we're still going. It'll take a minute or two. It's nearly there. Right, so let's just wander down. So, I can't do anything until this comes up. Good.
We're all hammering it at the same time.
Yeah, although you'd think that wouldn't matter, because
That's what this is.
I mean, this is all running in like Google's cloud. So
yeah, right.
they're essentially, sure, a bunch of the people in this room just connected to Colab, but that's a tiny blip on Colab's radar. And it's pulling stuff from GitHub, but once again, you know, GitHub's a big place. Right, that's done, that's run, so it took 2 minutes. So standard notebook blurb. So we import Firedrake. Probably at some point someone told you not to import stuff from things, and they're completely right, except that when what you're doing is effectively importing an entire language, it's incredibly tedious saying you have to prefix every word in the language with a namespace. So we do this a lot. So we are reasonably well behaved about giving you documentation. So everything that you see, so in the first place we're going to need a mesh. We give you lots of toy meshes. So we give you unit squares and boxes and the surface of a sphere and all those sorts of meshes. And for all of these functions, we've got stock strings and they'll tell you what to do. Usefully, all of the meshes also tell you at the bottom what the numbering of the boundaries is. So if you want to apply a boundary condition over only part of a boundary, you need to know where. If you're doing that in a mesh generator, well, you specify your own boundary labels. But if you're using a mesh that we gave you, you need to have them. We can also, you can do that in the sidebar as well. But actually, so let's make a mesh. And we give you plotting functions for meshes. So actually, the other way to find out what's going on in your mesh is you plot the mesh, so try plot mesh, and it's a little hard to see here, you'll see more clearly on your own one. These edges are colored, and over here it tells you what numbers correspond to which edges. So that when you want to supply a boundary condition in a bit, you can do it. So now I'm going to do exactly the same things that you saw in the Vertex equation. So I'm going to drop that on the floor. I'm going to make a function space. Now I'm going to do a linear finite element problem. So I have two unknown functions. I have the unknown test function and the function I'm solving for, which is called the trial function in finite element speak. So there's my test and trial function. Here's my spatial coordinates. This time I'm unpacking the vectors, so I get a scalar x and a scalar y. That's just Python, whether you unpack vectors or not. And here is my PDE, exactly the same syntax you saw before. The difference is that when we have a linear PDE, we specify both the left-hand side, and every term on the left-hand side has a u and a v, and it's linear in both u and v. And we specify the right-hand side, which is only linear in v. The secret there actually is you could have just specified this as a nonlinear problem, and under the hood we turn all linear problems into nonlinear problems. So this is actually only syntactic sugar for users who like to think about their problems as being linear. So we hit down and we solve. Now, you'll see this a lot. There's a solution going on. Over on the right, we have the solver parameters. That solver parameters is a dictionary, and inside that dictionary, we're actually programming in a whole different language. So those solver parameters are the solver language of Petsy. And that gets handed straight to Petsy for Pi. And that's how you can build up arbitrarily complicated solvers, just by passing them through to their levels. So as I keep saying, there's only one trick, and the one trick is that we can compose together things. And so in this case, we're composing Firedrake on top of Petsy. And I can look at my solution, and that's kind of useful. It's probably more useful to look at my error in my solution. So if you look, my solution goes from -1 to 1, and my error at this resolution is 5%. It's pretty small. So there are some exercises here. We're not going to do all the exercises because we're kind of set up here for doing whole day courses in Firedrake, and here we're just going to have a little play. But we'll do some of them. So what you should do now, just to have a play with this, is go back and solve this with quadratic elements. So what you need to go back and do is go back to the function space declaration and change it from CG1 to CG2. Now, at this point, you need to remember something about Jupyter Notebooks, something that's horrible about Jupyter Notebooks, and that is that the execution order in a Jupyter Notebook is not the order it appears on the screen, it's the order that you execute the cells in. So that means that when you go back and change the function space, you then have to re-execute every cell between there and here, otherwise Firedrake is going to get horribly confused because you're going to be using a mixture of old and new different ones. So I will attempt to shut up for a couple of minutes while you do that. If anyone has issues getting in, you can stick your hand up and I'll come and see if I can get you in. But I think it's usually pretty reliable once we're onto CoLab.
Is that supposed to contain /GitHub in the URL?
No.
Without GitHub. So there's two separate lines.
Oh, there's two separate lines.
Yeah, okay, sorry, okay, that's what I mean.
Once you click through there, I agree, we'll give you a URL that's got GitHub in it. But those URLs are really long. I wasn't going to let those up.
I wish you had a copy of what we're going to edit.
You can, but I mean, I'm assuming that you don't really want to permanently keep your immortal edits to these files. Yes.
Make sure that the main screen is reflecting this. Can we switch screens?
Oh,
They're not able to see the.
Oh, hang on.
Let's go.
Come out sync somehow. Oh, that could be. Where did that happen? That's weird.
So yeah, I think I don't control that.
Yeah, you.
Thank you.
I don't know. That seems an intermittent problem because Stuart did show me that. Deactivate and activate.
Got it.
Some guesswork here. Usually I remember to hand out software carpentry style ready to read stickers at this point, so people can tell me when they're done. Probably most people are sitting there watching 2 minutes of CoLab start. Yep. We used to do this by launching a Jupyter Hub in the cloud and handing out links to it, which had the advantage that you didn't have this 2-minute wait. It had the disadvantage that it was flaky as anything. And we would sometimes just lose the whole thing for an extended period while Amazon Web Services decided to lose its rag or something. So fortunately, yeah. Little wide, three little ones. Yeah, it's Firedrake project, not Firedrake. It's somebody else was named squatting Firedrake on GitHub before we got there. which is not as extreme a situation as the reason why it's Phoenix Project. The reason it's Phoenix Project is because it turned out that several years after Phoenix were up and running, some sort of trading firm, market firm that had registered the trademark Phoenix in the US, and suddenly decided they wanted to start using it and threatened the Phoenix people with legal action. And the compromise was they said, we won't sue you if you always call yourself Phoenix Project and not Phoenix. Sure. Yeah. Yeah, there are limits if you're not plugging together. Right, shall I show you how to do this? It's very simple. All I'm going to do is go all the way back up to where I define the function space. Change the 1 to a 2. Then I'm going to go down and tediously run all these again. And when I look at the answer, well, it looks a little bit smoother, but it's basically the same thing. But if I look at the error, it's shrunk enormously. So we were at about 5% error, and now we're at like 0.15% error, 0.5% error, which is spectral convergence, right? If you increase the polynomial order, then the convergence is exponential in polynomial order, so it'll go really, really fast, assuming you're sufficiently smooth. Which, of course, is useful for some problems and less useful for other problems. If you're doing a weather model and you have fronts, it's less useful. Right, so the other thing I could have done, which I will do, is go back all the way up to the inner square mesh and tell Firedrake to give me a quadrilateral mesh. And there you go, there's my quad mesh. And, oh, I'm not seeing, oh, it's because I wrote Lagrange. That's fine. If you're using discontinuous Galerkin methods and you go to quadrilateral meshes, you have to be careful about what you call the Lagrange space. Because for discontinuous meshes, there's 2 Lagrange spaces. There's a difference between so for degree 1, there's a difference between the linear and the bilinear space. You have to specify which one you're doing. For continuous, only the bilinear space exists, so it's not ambiguous, so we don't complain. So if I've written that, I would have got a warning. I'm not going to do that because the discretization I'm using isn't valid for DG anyway. So if I do this, and what I'm going to find when I do this, is that the error is even smaller again. So that is just because the cancellation is better, particularly on regular meshes. The cancellation is much better for quadrilateral elements. So that's not a higher exponent. They're both order h to the p squared, but the error coefficient is much smaller on quadrilaterals. That's why people like quadrilaterals. The reason you might not like quadrilaterals is that meshing inconvenient spaces with quadrilaterals is much harder. So we can kind of do both. Right, I'm going to jump out of here. How am I going?
I missed the how you set up the quadrilateral mesh.
I just told the mesh to be quadrilateral.
Just
so.
I see,
yeah.
like that. Okay.
So
yeah.
Yeah.
Is it possible to do like hybrid,
Not yet. It is in the the current round of funding we have, hybrid meshes is one of the things we're supposed to do. It's challenging on a couple of levels. So there's a bunch of infrastructure because now I have at least 2 classes of cell, and I have to generate different code for each one. And it's 2 classes of cell in 2D. In 3D, the set of different combinations of things that can touch each other is quite big. But that's just a, so I can kind of do that. The other thing that we need to think through is how to think about describing the function spaces in a high-level mathematical way. Because the function spaces on triangles and the function spaces on quads are not exactly the same. And it's not always completely obvious which ones you want to couple together. And so we have to do some maths thinking about what the right way to describe spaces looks like that.
If you do expect there will be benefits out of the inside space.
Sorry?
You do expect there will be.
Yeah, I mean, the reason why you want to use hybrid meshes is, so the people who like hybrid meshes are, for example, the aerodynamic people. And what they do is they tetrahedral mesh around their plane, and then further away from the plane, they use regular quad meshes because it's the aerodynamics of it. And so you could think about doing that, and it would be an interesting thing to do. There's certainly use in mind. There are related issues that we'd like to do with local peer review. So that's once again, that's not me.
No, might be me. Yep, there.
Oh, right.
If that's in there, is it?
Okay, so let me jump out of here. And okay, so I'm seeing the same thing that you're seeing, which is right, I might jump to this one because how am I going? What have I got for time?
You've got,
Yep.
35 minutes.
35 minutes. So we can probably do 2 more of these. Which ones do I? Actually, what I might do, because a bunch of the people, I'm presuming people here are kind of interested in the environmental end of problems. In which case, what I'll do is I'll jump to mixed Poisson, which is, so we have this menu of different things that we can do. And this one, I'll start that horrible download process running again and talk about what we're doing here. So what happens when I have more than one solution variable? So if I am solving fluids or solids, so if I'm solving fluids, at a bare minimum, I'm going to have velocity and pressure, and temperature, salinity, other scalars. And if I'm doing solids, then I might have stress and displacement, or it depends which formulation you use. But you tend to have more than one physical quantity which are coupled together. And usually those are tightly coupled, so you need to solve the whole system simultaneously at once. So what that looks like, well, it looks like, for starters, a set of simultaneous partial differential equations. So the simplest thing I can do is do a Poisson equation, but do it in mixed form. So I start off with this guy, Poisson equation, the simplest second order partial differential equation with some boundary conditions, and I substitute in a new variable, which is the gradient of my original variable. Now, the traditional notation for this, which is the one I'm using, comes from the solids people. And the solids people use U as their primary variable and sigma as their secondary variable. If you're a fluids person, U is the thing that takes the role of pressure. Sigma is the thing that takes the role of velocity. Which is, yeah, it's just like with the lowercase letters. The conventions don't always make sense. So what we're doing here is the PDE version of what you were taught in probably first year differential equations or maybe even high school differential equations, which is that you can always turn a second order differential equation into a first order differential equation by introducing an extra variable. That's all we've done. So there's my two equations. So what this would be saying is that the velocity is moved by the pressure gradient, and the divergence of the velocity is either nothing, or in this case it's a forcing function. So that would be incompressible flow. And I still have boundary conditions. I multiply by a test function, I integrate by parts. For the finite element aficionados out there, I'm going to use an HDiv discretization of the sigma, which is why I've integrated by parts to always get the divergence onto the sigma term and not on the other term. So I'm going to do HDiv L2. If you didn't understand the last two sentences, it's fine. It's not a big deal. So that has run, so that's ready to go. So I do the same thing again. This is exactly the same as what we did earlier. And now I'm going to declare my first function space, which is a more complicated one. This is a Rabiot-Thomas space. If you know what a C-grid is, those of you who've done maybe ocean or atmosphere modeling, Rabiot-Thomas is the finite element equivalent of the C-grid. So we have the variables are fluxes through the faces of the cells, at least at lowest order. And what would I do if I was doing C-grid finite volume? I'd have fluxes of velocity and pressure in the middle of the cell. Well, the finite element equivalent of pressure in the middle of the cell, as I say, is discontinuous, and it's 0th order. So it's just a constant over each cell. So I'm making finite element C-grid here, and so that's what those lines do. And now, in order to solve both of the problems together, what I actually need is a function space where for each point in space I've got a velocity and a pressure. And that function space is therefore the Cartesian product or direct sum of the space of velocity functions and the space of pressure functions. And we do that by doing algebra on the function space objects. So here, W is this function space times this function space. And now I can declare functions in W, which is formally what we're doing, because we're solving for something which has both components. But usually, we don't actually write out these functions. Usually, we write out U's and P's. So in order to give you mathematically what it was you were expecting to write down, I can pull out, this is for functions and test functions, I can pull out the different bits. And so now I've got my mixed system, but they've all pulled out of the same function space. So I'm solving them together. And so once again, I set myself a forcing function, and this is the PDE we saw earlier. Right? It's only one line. The reason it's only one line is because the test functions in the pressure part of the equation are orthogonal to the test functions in the velocity part. So this one and this one are tested with tau, which is the velocity test function, and this one is tested with v, which is the pressure test function. And so inside my code, I can always pull these two apart, because those are orthogonal. They don't affect each other. So we write down one system of equations, and there's our right-hand side. Our right-hand side is just 0 in the tau part, so we don't need to do anything there. And so we declare a solution variable. So now the solution variable is in the whole space. Right, so this is I'm solving for velocity and pressure, and I say I'd like to solve my system for velocity and pressure. Now I have to be a bit careful about how I do this. Our default solver is a direct solver, and direct solvers are going to scale very badly on a problem like this. So what I'm going to do to start with is just smack it with minres. So minres works on, it's an iterative solver which works on indefinite systems, because this is a saddle point system, right? So that's what's going to happen. And that's going to work. One thing to be aware of when we're looking at these things now, and you look at the time, so these are tiny little problems, so they're not very representative anyway, but also the first time you run one of these, it's spending quite a lot of the time in the compiler. So if you really want to know how long one of these things is doing, what you want to do is run that cell again, and you'll find that that was nearly instantaneous. So actually it was spending all its observable time in the compiler. So I can look at the answer. I have this split mechanism here. So split gets me the two different parts out. And so I can make subplots, and those subplots contain the different bits of the. So that's the solution to my equation. And so that's my pressure. If you remember, this thing has to be the gradient of the pressure. Plausibly looks like that is the gradient of that. All the lines pointing out into the maximum in the middle. So that's how that works. Now, if I were going to do this at decent resolution, especially if I were going to do it in 3D, minres would suck really fast. Right, this would be a really slow way of solving this problem. This is why the people who worry about solving this problem spend all their lives worrying about preconditioners. So how are we going to start preconditioning a problem like this? Well, first of all, I'm just going to do a bit of baby software engineering and give myself a function which makes the solver and does it as a function of the solver parameters, so that I can stop retyping 50 million Jupyter notebook cells. And the first thing I'll do is I will give myself a basic preconditioner of this problem. And I'll do this, and I will do it for increasing mesh resolutions. And so our original problem was on a tiny little mesh. You can now start to see what the problem is. Because even though these were all quick problems, this scaling is horrible. And the reason this scaling is horrible is that scaling is horrible. So if I start to ramp that up to a real size problem, that's going to become very unfun very quickly. If I'm the Met Office and I have to solve my pressure solve in a lot less than a second for a global weather forecast, I'm going to be very unhappy with what just happened there. That is, by the way, not an entirely academic point, because the function spaces we are working with here are very closely related to the function spaces the UK Met Office is using in the new model. Right, so what we do instead, so remember I have this saddle point system, right? So this is what my matrix looks like. I've got a velocity block, a velocity pressure block, a velocity pressure block, and a pressure block. And that makes this block and this block are essentially each other's transpose. So that produces a saddle point system, and they're quite hard to solve. What's easy to solve is a symmetric positive definite system. And the original Poisson problem was a symmetric positive definite system. So I've actually made things worse by introducing these extra variables, splitting them apart. Now, that's true, except that I couldn't write down my atmosphere equations in primal form. So I'm forced to be this way, but it does suggest what I can do to get around this. And what you can do to get around this is to substitute back down to one equation, and that one equation, it turns out, will be symmetric positive definite. That's called a Scher complement. And the way you make a Scher complement is you Gaussian elimination on these blocks, and that's what this matrix is. So you get these guys, they're easy. We have A and we have S. S is the tricky bit, because S is, say, CA inverse B. So when I write out some PDEs, I discretize them using finite elements or finite differences, non-spectral, that's different. then I get a very sparse matrix. The reason I get a very sparse matrix is because the test functions and trial functions are locally non-zero. So I don't get direct connections between degrees of freedom that are a long way apart in space. If I invert a sparse matrix, regrettably I do not get back a sparse matrix. So this guy is on. So the good news here is I've got a mechanism for producing a symmetric positive definite matrix. The bad news is I don't really, because I don't know how to evaluate it. So what you can do instead is you can effectively apply the thing inside matrix free, so that you just apply all of these solves. So it's the first thing I can do. It's an approach to the problem. And this is where PETSI becomes wonderful, because without changing my actual code, right, I'm still going to call the same create solver down here. I can provide different options to PETSI. So this says, treat the different equations separately, do a show complements. It's an approximate show complement, I won't go into that. And then on the inside, do conjugate gradient, because the inside problem is symmetric positive definite, precondition ICC. On the outside, do unpreconditioned conjugate gradient. Yeah, I know. Eyebrows have just gone up. It's not the best thing to do. We'll get better. Give me a chance. So the good news is, as I increased n, all of these converged in exactly 2 iterations. The bad news is this number, which is massively increasing over here. And the reason for that is because the preconditions are back. So I'm down to the point where my outside solve is essentially exact, but applying my outside solve is very, very inefficient. But that's okay, because there is a huge range of options that you can apply to do this. And I'm going to skip over the section where we go into details of that, because we're not really wanting to learn these. But one answer is to precondition S with this. So this looked like S, except that I've taken the diagonal of A. And the thing about taking the diagonal of A is that diagonal matrices have sparse inverses. And I'm not going to use that as S. I'm going to use it to construct the precondition of S. And that turns out to be a quite good precondition of S. And I can do that, again, by changing my discretization not at all, and instructing. So we're going to do the same diagonal preconditioner. I'm now going to, here's my inner solve, and on the outside now as well, I'm going to do an algebraic multigroup. Once again, no code changes, just tell PETSI I want one. One of the other beautiful things about PETSI is Hyper isn't part of PETSI at all. Hyper was written by, what's his first name, Firedrake, and about 20 years ago. And one of the beautiful things about PETSI is it pulls in a very large proportion of the solves that anyone anywhere in the world has ever written, and you can just get them by writing a couple of lines instead of by writing any code at all, or essentially any code at all. So let's do that. And, oh, that's the, where am I going? There we go. Right, so now, instead of scaling up to 10 seconds, I've scaled up to 1.3 seconds. So we're already a lot better. And I'm going further now. It's still not scaling perfectly. There is some fiddling we can do with solver tolerances that will make it a lot better. So now I've reduced my 6.4 down to a 2. And what I could then go on and do, but I'm not going to in this session, is stack up even more complicated sets of preconditions. So we have live cases that people use for real work with 4 or 5 preconditions set up. What you're doing each time is you're turning the problem into a somewhat easier to solve problem. You just keep doing that until you get to one that's easy to solve in your mind. So the last thing I think I want to play with is, let's go back and do the, let's go back and do the inverse problem. So let's get GitHub, no, not me. So it's here, number 6, PDE constrained optimization. First thing we do is run that again. So this is going to be another good example of this composition effect, where, is that right? Yes, it is. Where we reduce problems to simpler problems. And so one of the things we're going to do is solve an optimization problem where the constraint is that I satisfied my PDE. So in order to solve an optimization problem, I'm going to need an optimizer. And to make my life easy, I would not recommend doing this for serious real work. I'm just going to import SciPy and use one of SciPy's optimizers around Firedrake. Firedrake will talk to IPOpt, roll, Muller, Optizel, and so you can wrap it in a more grown-up and modern optimizer than the one I'm going to use. But if we just want to demonstrate, then only having a couple of lines is important. You don't need to pip install SciPy, by the way. We'll make sure it's installed in the environment we're using. So the problem we're going to solve this time is we're going to effectively solve a constrained Stokes problem. So here's my Stokes, and I'm going to minimize the compliance. The compliance is effectively the work done to bend the fluid. And this is a problem that comes from flow control. So what I'm going to do is I'm going to make a mesh which is a channel with a void cut out of it. I'm going to allow myself to suck and blow fluid in and out of that void in order to attempt to reduce the work done as it goes around the edge. And this is a model problem for things like smart wings that are supposed to be able to maintain laminar attachment in regimes where they would have detached and things like that. So as usual, I'm waiting for the fun and games while this thing loads. How are we going? Oh, I'm done. The gods are with me. Just give me 1 minute. Okay, so as previously pointed out, we import Firedrake and then we import Firedrake adjoint. And what that does is switches on all of the recording mechanisms. And we get ourselves a mesh. This is also going to do a very short download because we need, this time we're using a slightly less trivial domain. So I needed to use an actual mesh generator to make the mesh and I have to load the file from somewhere. So to do it in the notebook on the cloud, we have to download the file. And so this is my slightly less trivial mesh because it's now got a circle cut out. So we're going to apply inflow boundary condition there, outflow boundary condition there, release slip, I think, at the sides, and this boundary condition here is going to be the control limit optimization. So I'm allowed to set the flow in and out of that boundary in order to get the answer I need. So that's the forward problem. I don't think I need to go into lots of details, but it's the same sort of mixed problem as the one we looked at last. And here are my boundary conditions, including in particular one boundary condition which takes the value g. So I can set a boundary condition to a function value, and it will just take the value of the function on the boundary. Here's my equations. Here's my solver. This time, I'm going back to just telling you to use a direct solver. So in Petsy's world, a solver is an iterative solver. So if I wanted to use a direct solver, what I have to do is use the null iterative solver preconditioned by the perfect preconditioner. So that's what's going on here. And so this is just solving that Stokes problem. It's a steady Stokes problem, and what we're probably mostly doing at the moment is compiling, and then we get out the other end, and I can look at the solution. So what happens, as you'll be very unsurprised to hear, is the flow goes from the inflow to the outflow on. The flow goes from the inflow to the outflow, and it goes around here. And so it speeds up as it gets forced past the island. That's the point at which the island's effectively doing work on the fluid. And so you get this pressure drop across here, because that's where the work has to be done. Because in the Stokes equations, you can only do work if you have a pressure gradient driving the work. That's where the energy comes from. So that's what it looks like. And so now, what I do is I write down, so here is my functional, that's what this line here is. So it's the compliance, and it also, so that's the compliance here, that's the work being done, and this is effectively a regularization term. What this is doing is saying, and I don't want to suck in and flow very much fluid, right? So there's a penalty in the optimization for the size of that boundary condition. And that's a pretty common sort of regularization term. And I have to symbolically tell the optimization what the control is, and then I can make the thing I'm optimizing. And then this is a new thing I put in when I was in Australia, because I spent a lot of time in Australia debugging inverse problems, and I got sick of not knowing what was going on. So what that does is switch on the progress bars that you're about to see. And what I do is I tell SciPy optimize to minimize this functional. And so what's going to happen is SciPy optimize will, behind the scenes, it will evaluate the functional, ask for the functional's gradient. Using the functional's gradient, it'll update the value of the control and continuously do that until it decides it's done. And we can see it doing that on the outside, because every time I evaluate the forward adjoint problem, we're going to see it happen. So it's evaluating the functional. There are 11 steps to evaluate the functional. And so this number here is, remember I showed you earlier the graph? It's the number of nodes in the graph that have to be mapped out. So it's evaluating the first gradients. Notice how all the later ones are faster? It's because all the code generation happened the first time you went through. Okay, so it's done. What does that mean? Well, it means that the output, gopt, the optimized control, takes some useful value. So let's have a look at what the optimized control is. So the optimized control said, oh, well, suck in a bunch of flow at the front and some around the sides. Seems intuitively right. And what does that mean? Well, in order to know what it means, there's a couple of things we can do. One of them is we can see how much better did the target functional get. And so the reduced functional is a function, and you can pass in a control value to get a function. So here's my initial value, here's my optimized value. So if I do that, and you'll see it's evaluating the functional twice, and it tells me that the functional went from 48 to 19. I don't know if 19 is optimal, but it's certainly better than 46. And I can also solve the system for the new value of G and have a look at the answer, you'll notice that annotate false at the end here. So that's an instruction to the solve to not record this solve because it's not part of the full problem. Otherwise my tape keeps getting longer and longer and longer. And if we compare what's here to what was done up here, we see it's a very different looking setup, and in particular the pressure drop is a lot lower because a lot less work is being done. And so that is in some senses the right thing to do. So I'm going to shut up there because it's about 6 minutes to the hour, and I will take questions. I can see one's already coming over here.
Where did you set constraints for this?
So that is an unconstrained optimization problem. The answer to where you would set constraints is, well, there's two answers. So you can use a Lagrange multiplier to turn your constraints into unconstrained problems and feed into any optimizer. Or if you want to have, in some sense, hard or strong constraints, then that one's actually not Firedrake's problem. That will be different for each optimizer because it depends how the optimization algorithm applies constraints. Right? It's not. So Firedrake's job in this game effectively is to solve the PDE and to evaluate the gradient function. And then constraints on the optimization process belong to the next layer of software out. And some of the pieces of software you can wrap around this will take constraints. So it's an available option, but it's somebody else's problem. Everybody wants submission.
So I was kind of interested in how this might fit in with a sort of wider, larger modeling work. Like say I was doing, I don't know, some kind of GCM or at least some idealized model or something. How can I sort of put this together with some other things, couple it with some other models? Yeah, I'm just sort of wondering about how I would go about integrating this into a larger.
Okay, so it sort of depends, right? So there is a outfit out there called Precise, which is the nth attempt in the world at a generic coupler of everything. And Precise does allegedly, I haven't tried using it, but Precise does allegedly have a Firedrake layer to couple in. What that would get you is coupling of coefficient values at points. That's about as good as ever anyone's got if they're not using a really customized, very expensive to code coupling system. But it's also not really nice or right. So what would be really, really nice is if you were, so one of the magic things about finite element is, unlike say finite difference, we don't just know the value of particular points, we know the value of functions everywhere. And that means that if what you wanted to do was integrate the coupling over, say, the boundary between an atmosphere and an ocean, mathematically we actually know how to do that computation. But what that requires is some code that would match the abstractions of the two software so that you can do that across there. And nobody in the world has done that. It would be awesome if someone did, because that would really change things. So at the moment, I'm not aware of anyone who's seriously using Firedrake coupled to something other than Firedrake. There are some people who do Firedrake coupled to Firedrake, and at the moment that's a bit hacky, but does work. We are probably a year off really nice Firedrake to Firedrake coupling actually really working well. But it does, I mean, Firedrake does work as the basis for an Earth system model component. I mean, there's, yeah, I showed earlier some of them. Probably Thetis, which is the coastal ocean model, is the most complete one that people use most out there for kind of fairly serious science work. Yeah, I realize if they run Anyone else need more? Ah.
So why does Firedrake not support OpenMP? You always have to set OMP non-threads to block. Why is that?
Okay, so the reason why we set OpenMP non-threads to 1 is because OpenMP has literally the stupidest default ever created in the history of computer science.
Can I cite you on that?
Yeah, yes, Ham 2022, which is that if OpenMP is linked into your application, it will by default spawn a number of virtual cores threads and fire them off, which, given that Firedrake is MPI only, is catastrophically dumb. And it's really bad behavior by OpenMP. OpenMP should default to 1 thread unless told on. It's really stupid thing to do. So that's why that's everywhere, is to stop that happening. Okay, why do we not do OpenMP threading? Well, the proximate reason is because PETs don't, and we're all in on PETs for all our data structures and so on. However, I also know why PETs don't, and I wholeheartedly agree with them, and that is because it doesn't actually help. It doesn't fix any problems that you've got. And the reason, effectively, is that the difference on Linux, effectively, which is the only thing that counts, all the supercomputers Linux. The difference on Linux between a thread and a process is almost nothing. You actually make the same syscall to make a thread as you make a process. The difference is that a thread has by default shared memory and a process has by default distributed memory, but you can get out of it, right? So a thread can declare variables as private, and there are various shared pointing mechanisms for getting shared memory between processes. Default shared is error prone as anything. The reason why the people who program NP spend all their time staring into bugs is because of sharing this. And actually, when you're doing this sort of problem, we have a small number of large, well-known shared data structures, and everything else should be completely private. So, the OpenMP argument is, but we can strong scale that because you don't have to do the halo exchanges. The halo exchanges are almost never the problem. Usually, actually, when we are strong scaling, we run out of strong scaling ability to solve it before we run out of anything else. So it's just not going to help us. Even if it did, then I would strongly argue that you should rewrite your data structures to use MPI shared memory instead of using OpenMP. But we don't, and PETI don't, and as far as we can tell, it never helps us do that. And in fact, like number of real-world cases of OpenMP plus MPI being straight MPI is vanish. It essentially never happens. Certainly not for solving these. It is already gone through, just up slightly, but I think we should probably wind this up. There's plenty of, I'm here all evening, so there's plenty of opportunity for people to harass me in the meantime.